Okay, so this week we're going to be doing hypothesis testing, which is more based off a sample. What can you say about a population? Just like with confidence intervals and how we were making estimations of the mean, of the population mean based off the sample mean. So this time we're going to do hypothesis testing. This is probably the longest well, it's not probably anything. It is the longest thing that we do. There's several steps involved, but as long as you follow each step, usually you can come up with the right answer. So I'm going to have the video for notes, and then the notes follow along with the PowerPoint as far as definitions go. I'm going to just do them on the notes page so that I can do the problems and explain those too. And then there'll be a couple of videos that explain different parts of hypothesis testing, so then you can kind of put it all together for the homework. So I'll give it to you. The notes does everything, and then I'll give you a couple pieces just so you can practice certain pieces at a time. And so you'll actually have 2 weeks to complete this, this unit, just because it is a little more time intensive. So to get started here, we have a hypothesis is a claim or statement about a property of a population. And then a hypothesis test is a procedure for testing a claim about a property of a population. So we're going to have, you're going to make a hypothesis about the population, and then you'll actually run a test to test that. So you have two types of hypotheses. You have what's called the null hypothesis, which is denoted as an H sub 0. It contains a statement of equality. You have equal to, less than or equal to, or greater than or equal to. If you do this for a living, if you're a statistician or do any stats for a living, you would only ever use the equal to, but for the class, we're just going to use any of them. And then the other one is called the alternative hypothesis. It's denoted with an H subscript 1, and it contains a statement of strict inequality, so not equal to, less than, or greater than. So the first thing that you're going to do for all these problems is you'll read the problem first, and then you come up with what is the problem claiming. So you have to figure out what the claim is, and then you'll write down your hypotheses. So this first part, you want to write the claim about the population, write its complement. These are complements, null and alternative. They're basically opposites of one another, and label the claim. And your claim can be the null hypothesis, or it can be the alternative hypothesis. It doesn't have to be one or the other. So a hospital claims its average. Anytime you do average, and this is what I do, I write claim, and then I'm going to write what it says. Average, we're talking about mu for population mean. The average mean is mu. Ambulance response time is less than 10 minutes. So they claim that the mean is less than 10. So that's your claim. So for the first thing for all these problems is you want to write claim and write what it is. That way you don't get confused later. So then to write your hypotheses, you've got H sub 0 for your null and H sub 1 for your alternative. So you have to look, you have to put the claim where it goes first. So H1 is the one that has strict inequalities, not equal to, strictly less than, or strictly greater than. So this is a strict inequality, so it's going to be our H1. So mu is less than 10. And then usually what I'll do, I know I've wrote it twice here, but you'll see why when we actually do a whole problem, I put in parentheses claim, just so I can remember, okay, that was my claim. And then to come up with the other hypothesis, you do the complement, or the opposite of this. So if this is less than, then this would be greater than or equal to 10. And this is where you should always, if you do this, you know, for a living professionally, you do just equal to, but for this class, we're just going to do the opposite and call it a day. So that's all we want to do there. So for number 2 then, first you're going to write your claim again. A consumer magazine claims the proportion, so for portion we use P, of cell phone calls made during evenings and weekends is at most 60%. So at most means it cannot be over 60%. So 60% is the highest. So P would be less than or equal to 60%, or you can switch to decimal form 0.60. So write your hypotheses. You have H sub 0 and H sub 1. This one has an equal to, so it goes with H sub 0. And that's our claim. The opposite of less than or equal to for H1 then would be strictly greater than. So there's your two hypotheses. For number 3, we have, as stated by a company's shipping department, the number of shipping errors per million shipment has a standard deviation, so standard deviation, sigma, that is less than 3. So this doesn't use the word claim, but it says, as stated by the company, the number of shipping errors has a standard deviation that is less than 3. So that is the claim. So sometimes you'll see the word claim, sometimes you won't, but it would be kind of implied. So less than 3. So do your two hypotheses. It's a strict inequality, means it goes with H1. And the opposite of less than for H0 would be greater than or equal to. For the last one, a study claims that the mean, so we're doing the mean again, survival time for certain cancer patients treated immediately with chemo and radiation is 24 months. So this time it actually says the claim is that the mean is 24 months. So is means equal to 24. Do our hypotheses. We have an equal to, which means it goes with H0, so our claim is with H0. And the opposite of equal to is not equal to. So for the first part of all these problems, you're going to write down the claim and you're going to write down your two hypotheses. So that would be step 1 when we get to actually doing a problem. So this is more, this chapter section is also a lot of reading comprehension, just like the last one too. So what we do then is once you have your hypotheses, you begin the test by assuming the equality condition in the equality one is the null hypothesis is true. So you start off assuming that it's true. And that doesn't matter if your claim is in the null or the alternative, if I could talk, hypothesis. You just assume that the null one, the H0, is true. Then you collect data from a random sample taken from the population and you calculate your necessary sample statistics. If the sample statistic has a low, and there's going to be a way to check for this so you can determine if it's low or not, low probability of being drawn from the population in which the null hypothesis is true. That's a lot of words, but I'll explain it when I do a problem. You will reject HO. As a consequence, you will support the alternative hypothesis. So if you reject your null hypothesis, then you're going to support this alternative hypothesis. If the probability is not low enough, you do not say that you support HO, you just say that you fail to reject it. So failing to reject HO is not the same as supporting. It just means that you were unable to eliminate it, but it doesn't necessarily mean that you're supporting it. So that's the part that gets confusing, but I set the problems up and I'll give you little hints. And so you write words, keywords next to your problem, and then you'll know what words to use. So you'll see it in just a minute when we get there. So we have what is called level of significance. So the level of significance is alpha. This is the maximum probability of committing what is called a type 1 error. And that occurs when you reject the null hypothesis. I don't know why I can't say that today. When you reject the null hypothesis, even though it's true. So obviously in statistics, it's not an exact science. There's a lot of estimations and certain calculations that you make to try to get as, give the best information possible. And sometimes, you'll say that like when we were doing the confidence intervals for, you're 90% confident that the mean's between these two numbers, but it may very well not be. So the same thing here, you may reject a hypothesis and it actually might be true. So it's still not exact. And then this says recall, it shouldn't say from chapter 7, gotta fix that. It's recall from our last topic, our confidence intervals, that alpha is the area in the tail or the tails of the distribution. So just for a little recall, here's our normal curve. If we have two tails here, let's say we were 90% confident, then remember alpha was the area in the tails, so that would be 10%. And we said alpha divided by 2, so 5% would be here. That was alpha divided by 2, and that was 5% here is also alpha divided by 2. So this is what our alpha is. It's in both tails. Or it may be if it's on the left only, it's in the left tail. If it's on the right only, it's in the right tail. So that's what we're getting into now. So that's still alpha is the same as it has been. And I guess that's been true. We've been doing alpha. We've been doing the area and the tails for more than just the last topic, so I could just say previous topics here or something, but I'll fix it. So you have different types of hypothesis tests. You have a right-tailed, a left-tailed, and a two-tailed, and they are what they sound like. The way to determine which one it is you look at your alternative hypothesis H1. So for a right-tailed test, your H1, your alternative hypothesis, will be, and I'm just going to use mu here. It could be mu, p, or sigma, but I'm just going to go with mean. It would be, H1 would be whatever population parameter we're talking about. So mu, for example, is strictly greater than the value. So for a right-tailed test, you have this over here is what we're talking about, and that would be alpha. And this is just supposed to be a standard normal, so mean 0. For a left-tailed test, your H1 will be strictly less than whatever value. So that would be alpha. For a two-tailed test, you can probably guess we've done greater than, less than. Now what's left is not equal to. So then it would look more like my picture I drew up there. You'd have both tails shaded in, and alpha is the area amongst two of them. So this would be alpha over 2, and that would be alpha over 2. So to determine the type of test, you look at H1, and that tells you what type of test you have. So we're going to, on this part, these two questions, determine whether the hypothesis test for each claim is left, right, or two-tailed. So first we have to write our claim and our hypotheses before we do anything. So like I said, for these problems, I always start with claim first. The standard deviation, so we're doing sigma. And by the way, when we do problems, we're not going to do any standard deviation problems. We're only going to do means and proportions on the whole problem drawn out, because they just take so long. So mean and proportion is all we're going to be doing, but for these we can use standard deviation. The standard deviation of the payment for the upcoming toll road is no less than $1. So no less than $1 means that the dollar is the minimum amount. So we would be claiming, or this whoever is claiming, that sigma is greater than or equal to, which means no less than $1. So write your hypotheses. This has got an equal to on it, means it goes with our null, or HO. Sigma is greater than or equal to $1, that's our claim. Which means our H1 then is the opposite of that, or its complement. So the opposite of greater than or equal to is less than. Then to determine the type of test, we look at H1. It is less than. So less than means it's a left-tailed test. For number 2, we have the mean life. So our claim is something about the mean of a certain tire is greater than 50,000 miles. So the mean is greater than 50,000. Write your 2 hypotheses. This one is strictly greater than, so it goes with H1. Which means the opposite of greater than is less than or equal to. And again, to determine the type of test, we look at H1. If it's strictly greater than means it's a right-tailed test. So that is how you determine the type of test it is. If we'd had a not equal to, it would be a two-tailed test. So you also have in this section what are called p-values. They're going to be the same thing as when we were doing the areas under the curves. You know, when we were using our standard normal probability chart that I posted a couple weeks ago. We've been using that chart for a while now. It's the same sort of thing. P-values are going to be those same areas. It'll be also like alpha, it'll just be in the tails that you're going to be talking about. It's not going to be in the middle anymore. It'll be in the left tail, right tail, or both tails. So it's called a p-value. We've been saying the probability or area, but now we're going to call them p-values. It's still going to be the same idea. So the p-value is the probability of obtaining a sample statistic with a value as extreme or more extreme than the one determined by the sample data. It is the area in the left tail for a left-tailed test. It's the area in the right tail for a right-tailed test, and it's the area in both tails for a two-tailed test. So you may be thinking, well, why do we have alpha if that was the area in the tails, and now we've got p-values, and that's also the area in the tails, which is true. There's actually two ways you can do these problems. You can use alpha and get critical values to do these problems using our inverse norm like we've been doing before, or you can also use test statistics and p-values. Either way, you have to get a test statistic, but you can also do it with p-values. So there's two ways to do these problems, and that's why we're talking about alpha and we're talking about p-values. I'm going to show you both ways that you can do it by hand, but then the calculator, you can actually run these tests on the calculator. It makes life a lot easier, and the calculator actually gives you the p-value, and then you can just use it, so it makes it a little bit easier. So that's why we're talking about p-value being the area in the tails and alpha being the area in the tails. So it all kind of makes sense once we put it all together. So we want to find the indicated p-value, the test statistic for a right-tailed test. So you can draw a picture. Right-tailed test is 1.56. So here's 1.56, there's 0. So your p-value is the area in the right tail here. So if you want to use normal CDF on the calculator, I don't think anybody was doing that. You can. If you want to use the chart, that's fine. To do the area to the right, remember you have to subtract from 1. So we would have 1 minus, if I go to my chart here, 1.56, same chart we've been using, 1.5 over to 0.06, 0.9406. 0.9406, so yeah, that's what I said. That is equal to 0.0594. So that is your p-value. And I'm pretty sure if you use normal CDF on the calculator, you get the same thing. What's a little bit different is when we do a two-tailed test, the test statistic for a two-tailed test, so that means the area in both tails. So for the right and left, it's the same. Use the chart. For the left, you do use the chart directly. For the right tail, you subtract from 1. That's the same. For a two-tailed test, it's a little different because what we've been doing is, so we've got negative 2.63. Still symmetric. That rule still applies. So this is positive 2.63. Zero's in the middle. But what we've been doing is, if you ignore my shaded part for a minute, we've been finding the area between those two. We've not been finding the area on the outside. So we've been only finding this. So now this is where we're changing it just a little bit. P-value is the area in the tails, not in the middle. So when we were doing confidence intervals and that sort of thing, we've been doing what's in the middle. Now we're going to do what's on the outside. So the easiest way to do that, in my opinion, is this one down here is negative 2.63. That's to the left. Well, what is that value? Go to your chart on the negative side. So negative 2.63, we got negative 2.6 over to 0.03 is 0.0043. Because the chart gives you the area to the left, so you can look at that side and just write it down from the chart. That's, pretty straightforward. We've been doing that. So we've done, I'll take that away. We've done this, so that's fine. So what has to be true about the standard normal? They're symmetric. These two areas have to be the same, which means if this is 0.0043, then that also must be 0.0043. Which means, what is your p-value? Well, you just add them two together, or multiply 1 by 2, however you want to think about it. So the p-value is 0.0043 plus 0.0043, which is 0.0086. So in my opinion, for the two-tailed ones, to get the p-value, it's easiest just to look up the left-hand one, and then you're doubling it to get the area in both tails. So that's a little bit of a tweak since we've been doing the area in the middle. Now we're going to do the tails. And when you do these, if you use normal CDF on the calculator, that's fine. You can do 2 times the normal CDF on the calculator. Your last decimal may be off by 1, but like I've been saying that over and over. If your last decimal is off by 1 because you use the calculator, that's not a big deal. So that is how you find p-values. Let's see if I can figure out what I've got my papers in order here. So the next part is making a decision. So this is whether or not you reject or fail to reject. What I was kind of hinted at that a minute ago. So the decision about whether there is enough evidence to reject the null hypothesis can be made by comparing the p-value to alpha, the level of significance. If your p is less than alpha, then you reject the null hypothesis. If p is greater than alpha, you fail to reject the null hypothesis. So when you make a decision, it's always about the null hypothesis. The decision may also be made, this is where I was saying you got 2 ways to do this. You may also make your decision by comparing your critical value, that was what I was talking about using the inverse norm, to the standardized test statistic. And I'll show you both ways so you'll see this. If the standardized test statistic is inside the rejection region, you will reject the null hypothesis. And if your test statistic is outside the rejection region, you will fail to reject the null hypothesis. Now, the way that you teach college kids to remember this, because I've taught this in, just regular college, like with, 18, 19-year-olds. is you do P to alpha, and you say if P is low, most adults find this funny too, then you reject the HO, but they don't say HO, they actually say the word, so it rhymes, and then they get all tickled, but they actually probably still remember it 5 years later. So if P is low, you reject HO. So this next part, we're going to practice making a decision. So it tells us the p-value of a hypothesis test is 0.0749. Make your decision at the 0.05 level of significance. So your level of significance, this is always alpha. So what we want to do is compare p to alpha, so 0.0749. If it gives you a p and it gives you an alpha, then do it that way. And alpha is 0.05. Well, 0.0749 is greater than 0.05. Well, if P is low, you reject. So, since it's not, we fail to reject. Fail to reject HO. If P is 0.0246, what is your decision if alpha is 0.05? Well, again, compare P to alpha, 0.0246. Compared to 0.05, 0.0246 is less than 0.05, so P is low. That means you reject HO. Same p-value, but alpha now is changed to 0.01. Okay, same thing. Compare P, 0.0246, to alpha's 0.01. Well, 0.0246 is actually greater than 0.01, so if alpha's 0.01 instead, you would fail to reject HO. So these alphas correspond to, this one corresponds to a 95% confidence interval. This one corresponds to a 99% confidence interval. So this one allows a little bit more room for error than this one. So that's why on one you would reject, one you would fail to reject. Because remember, alpha is the probability that you actually commit that error of rejecting when you shouldn't. So that's how you compare P to alpha. You just look, if it's less than, you reject HO. If it's greater than, you fail to reject HO. The next two deal with how to do it with using the critical value and the test statistic instead. So this is the second two are the other options. So if there is a two-tailed test, so we can draw a picture. And alpha is 0.05. So we've got a two-tailed test. Alpha is 0.05. That is the, if it's two tails, this means that alpha is the area in both tails. And it says find the critical value, and then it asks what's your decision if Z is 2.01. So if alpha is the area in both tails, it's 0.05. That means that if we divide that in half, we get 0.025 on the left and 0.025 on the right, because it doesn't look symmetric, but it's supposed to be. So how do you find a critical value? Just like we've always done, we found a critical value. And that's still in the same notation. If you want to write Z sub alpha divided by 2, that's fine. So we do the inverse norm of the one to the left, so 0.025. And you should get negative 1.96. So this critical value is negative 1.96, and then you also have the positive one, since we're talking about a two-tailed test. So that's normal. We've done that a few times, so that's the same thing. Only part we're adding is it says, what is your decision if Z is 2.01? Well, where is 2.01? 2.01 is to the right of 1.96. So that is, Z is 2.01. So it's inside that shaded region. So your shaded region is your reject region, your rejection region. So if it's inside this region or this region, either part you have shaded, you reject HO. If so for this one, for 2.01, we would say reject HO. If it had asked you what is your decision if Z is 1.70, 1.70 would be outside that rejection region, so you'd fail to reject. So for critical values and your test statistic, you just look. If it's inside your shaded part, you reject. If it's outside, you fail to reject. So for number 4, if there's a right-tailed test, so we're doing a right-tailed test, and alpha is 0.05, that means that alpha is the area in the right tail for a right-tailed test. It's in the left tail for a left-tailed test. Find the critical value, okay? So this is 0.05. If this is 0.05, this down here is 0.95. So our critical value is inverse norm of 0.95, which is 1.64. So this is 1.64. Says, what is your decision if Z is 1.75? If Z is 1.75, that's to the right of 1.64. So that means it's inside this shaded part here. The shaded part is still the rejection region. So if we're inside the rejection region, we're going to, again, reject HO. If it had asked you about, say, 1.61, that's outside that rejection region, that shaded region, so you would fail to reject HO. So that is how you decide using P and alpha, or decide using your test statistic and critical value. So I think this is actually where we start the examples and go through all the problems. So I'm going to stop the video here and then make a second video so that the definition and all the pieces were like one part and then all the problems are together. That way you'll hopefully have an easier time finding what you're looking for when you go through these.